Good morning, John. This is your friendly phys ed. Problem number 13. You're given a physical pendulum, and they tell you that you have a rod of length L and mass M. They give you numbers for those, both the length and the mass of the rod. And same thing for the disc. It's a mass M, it has a radius, and the center of the disc is located some distance d below the pivot of this pendulum. So they tell you that the clock keeps perfect time if the period's 3.5 seconds, but in Grandma's house, the period is only 2.5 seconds, and ends up telling you that the clock loses 5 minutes a day, and you have to adjust where the disc is located to get the clock back in sync again, keeping perfect time. So for part A, you're supposed to find the distance d if the period is this 2.5 seconds, if the clock is off. And then for part B, you have to adjust where the disc is to get the clock corrected. So model the physical pendulum and set up the simple harmonic oscillator equation from which you can read the angular frequency, omega. And then we know that the period is 2 pi divided by omega. That will be the key. Okay, so with the given information, what we're supposed to find, and now the plan in place, we start doing the analysis. Now I would model this using our friendly Newton's second law for rotation. Torque is the rotational inertia times the angular acceleration. So because the torque is a restoring force, I put a negative sign in front. The moment arm for the rod is L over 2, assuming that it's homogeneous and uniform as they say in the problem. So the center of mass will be at L over 2. That's where the force, gravitational force, is acting. So L over 2 times that force, moment arm times the force, times the sine of the angle, which is going to be theta, the angle of which we're assuming is a small angle, to which you push this pendulum to begin with. The moment arm for the disc is d, so d times the force, capital mg, times the sine of theta. That would equal the rotational inertia. Now we have to do the rod pivoted about its end, so that's a third its mass times the length squared. And then you have to use the parallel axis theorem for the disc. The rotational inertia about the center of mass is 1/2 capital mr squared, that's the radius of the disc squared. And then it's located a distance d away from that pivot point. So the mass of the disc times d squared finishes the parallel axis theorem. So add all those together and you have the rotational inertia for that whole system, disc and rod. Then you multiply it by the angular acceleration, which is the second derivative of the angle with respect to time. Rearrange that into our simple harmonic oscillator form, and you can read the angular frequency squared directly from the equation. So then set up the period, which they tell you is 2.5, as equaling 2 pi divided by omega, so take the square root of what we see in that simple harmonic oscillator equation. Plug in the numbers and solve for d. Okay, so finally here, if you're interested in seeing number crunching, here it is. You end up having to solve a quadratic equation for d, and I end up with a distance for this incorrect period of about 1.6336, so 1.63, 1.64 meters is where the location of the disc is when the period is 2.5 seconds. Of course, for the last part, you just set the period equal to 3.5, go through the same number crunching, and you get the corrected distance, and then figure out how far you have to move it to get to the correct distance, up or down. And that would be it. Have fun.